Morning. I'm Hugo Patterson. I am CTO and Founder at Datrium. I come from most immediately EMC by way of and data domain, where I was the CTO and the first engineer hired over there. Prior to that, I was at NetApp, where I built SnapVault and kind of got the first fat SATA drive filer going. But today I want to talk about Datrium and start off sort of hitting what the long-term vision is for Datrium before diving into the DVX and its internals. But the idea is that the ideal cloud is something with infinite capacity that's geographically distributed, provides access to data wherever you are at good performance, and you don't really have to worry about it. And data is protected all by that. But ultimately what we're building is infrastructure to make that possible. But for scalability and fault containment, you don't just have one ginormous system, you have a bunch of individual building blocks. And with Datrium, that building block is the individual DVX Rackscale system. And then the data cloud software is what ties them together into that larger cloud infrastructure. At that point, the cloud is the system. But what I'm going to start off talking about is the individual DVX. But keep in mind that the idea is that these eventually will tie together and extend even to the public cloud with a virtual DVX instance that can be part of the overall cloud ecosystem. And the goal is to make all of this effortless, or as close to effortless as possible, and allow administrators to focus on the VMs and applications that really provide the value to their organization and spend a lot less time worrying about the infrastructure that keeps it all running. So that's really at a high level where we're headed. But let me talk about one of those individual DVX Rackscale systems here pictured. And this is sort of the, if you put a quote together, that's kind of what you're quoting. And it is a pod, if you will, that consists of converged infrastructure that includes the compute to run the virtual machines. But also we use that compute to run the data management and the storage management functions. And it also includes dedicated data nodes, which store the durable data. And that is a unique feature of the Datrium architecture, right? So traditionally, but let me more on that in a second. On the compute side, you can buy a turnkey system from Datrium that includes Datrium compute nodes, but we are open converged in the sense that because of our unique architecture, we're able to support a mixture of servers within the same DVX. And that allows us to support third-party servers in the same system. So those third-party servers could be ones that you already own, and you want to upgrade to a DVX, but you don't necessarily want to toss out all of your existing servers, so you can upgrade them and leverage them. Or maybe you have particular requirements. You need a beefy quad socket, or you need some server configuration that we don't offer. That's fine. You can buy one or two of those on the side and have the rest be Datrium compute nodes. So we allow that mix and match, and that's really a result of our unique architecture that can support that heterogeneity of server configurations. So So we have the compute nodes and the data nodes, and let me just give you a better idea of what's where, because those data nodes are not traditional arrays, right? And so exactly how this breaks down is shown in this chart, which shows for 3 different styles of converged infrastructure where the core functional pieces sort of reside, and hopefully this will help you understand how the DVX architecture is really unique out there, right? So in the first Rev 1.0 of converged infrastructure, the people just took traditional arrays, existing servers, VMware, and a little bit of management duct tape to tie it together, and that was converged infrastructure. In that case, of course, the processing for the applications and VMs was running on the servers, but traditional arrays have controllers, often quite beefy controllers for doing the storage processing, for doing the compression if it's supported, for doing deduplication if it's supported, maybe encryption, RAID, erasure, all of that stuff. Snapshotting, replication, all of that stuff is performed by the traditional array controller. And also, if there's flash, well, it would just be another device type within that array. And of course, there's the durable data on the shelves of disks or SSDs inside. 2.0 for converged infrastructure was hyperconverged, and all of these functions that I just described were sort of smushed together into the same server platform. And so in that case, you have sort of one kind of node connected by a network, but that node runs the VM workload, it runs the I/O processing as well. If there's flash, it's devices in those servers. And also the durable data is also included in that same package, right? So Datrium factors this set of functionality differently from either of those. And so it leverages the host compute for all of the compute functions, and that means for the VM processing, the application processing, but also for the I/O processing, the storage processing. So in the Datrium DVX, compression, deduplication, RAID, erasure coding, snapshotting, replication, encryption, all of that is performed inside of those compute nodes. And we leverage flash inside of those compute nodes for performance. Data is always local to that server for the applications running in it. So you get the latency of direct attached flash inside of the server and the IOPS that delivers. But we don't put the durable data inside of there. We break it out into dedicated data nodes and then have an architecture for the software that allows all of the hosts to operate independently of each other. So there's not a lot of chatter amongst them. And there's a lot of really nice side effects. You know, once you have this separate data node, it relieves a lot of pain points of a hyperconverged architecture. So in this picture, we show what happens in the hyperconverged, right? So I'm just going to hit on this point a little more with a fancy animation, which Craig put together for me, which in the hyperconverged, all the functionality is in one place. And as a result, right, to achieve, for example, reliability, when one server does a write, it needs to send that data off to a couple of other servers. And depending on the specific hyperconverged implementation, reads may also come remotely. So there's a lot of node-to-node chatter, and as Brian mentioned, servers become part of the storage infrastructure. So you kind of have to manage them as carefully as you used to have to manage storage. The servers are no longer stateless, which can create a management challenge. Because it used to be you could walk up to a server and do whatever you needed to do on it, yank it out, replace its NIC, and not worry about it. But in Hyperconverged, that's no longer the case. So we address this by pulling the durable data out of the hyperconverged nodes, out of the servers, and into dedicated data nodes. But we leave the rest of the processing, the non-persistent part, in those servers. So yet the servers still do the VM processing, run the applications. They still do the storage management functions, and there's local flash inside the servers. But the servers are now stateless again, and they are independent of each other. So there's not a lot of cross chatter, just like they used to be. So you can now manage the servers just like you always did, but you get the benefit of having that scalable IOPS and performance that was the thing that you most liked about the hyperconverged model. So just to hit on that, right? The performance part is in the servers, right? Because every server comes with more storage compute. It comes with more cores, more cycles to run compression, encryption, deduplication, erasure coding, replication, all of that. And it comes with more flash, so there's more raw IOPS capability in the DVX. And as you add servers, you get more of that, right? So one of the big challenges with a traditional array is that controller that it comes with is sort of a fixed resource. It's a fixed pie. And the more servers you add, the finer you have to slice that pie. And the beauty of server-powered approaches, whether it be hyperconverged or the Datrium matrixed architecture with these two dimensions of compute and durability, is that as you add more servers, you're adding performance. It's like a controller upgrade with every server you add. And so we have that benefit as well, being server powered, because all the performance comes with the server.
Okay. So how do you handle, one of the issues that hyperconverged hits from anybody and other type of similar solutions such as Pernix data on this is metadata scaling. How wide do you guys scale? Where's your performance cliff? Where do we start hitting issues with scaling these, compute/controller nodes and then having to worry about tracking metadata, dedupe operations, that sort of thing?
So the question is how well these things scale, and so there's a couple of different kinds of metadata. And let me just sure. Click one more click and then answer it. And I would just say in our next release coming soon, you can also independently scale the capacity nodes. Okay. All right. So if you need more performance, you scale the compute. If you need more capacity, you can scale the data nodes. And so you can scale those independently. Now, as you scale the capacity, you're also scaling what is necessary to manage that capacity. So from a dedupe standpoint, for example, the index scales with that. So every data node is scaled to address the amount of metadata that's necessary for the capacity that it delivers. And so those capabilities scale linearly as you add data nodes. Things like index size is a function of data capacity. And so that scales there, as well as NV logs and the ability to manage other metadata. The one thing that we don't scale right now is things like the namespace, but this is not a big deal in a virtualized environment where the files are virtual disks that are typically many gigabytes to terabytes in size, and there's typically only in the thousands of them, and that's really not where the load is, that it doesn't really need to scale at this point.
What's your largest deployment that you
Well, today, as I mentioned, we're shipping with one node, and so that would be our largest. Our smallest, our only deployment with one data node. And we have at least one customer running regularly with 28 servers connected to that one data node.
Okay. So if I asked Nutanix or VMware vSAN team or SpringPath team, how do you scale out? They all tell me we scale linearly. You add nodes, you get more capacity, you get more compute, you get more performance. But I think we all know that that is not the case. I hit points where latency goes up. I hit points where metadata scaling becomes an issue.
So we don't claim it scales infinitely. We support 32.
Okay.
We support 32 servers per data node. Yeah. So as I mentioned, each of the data nodes comes with in hardware. It looks like a very standard vanilla piece of storage hardware in that it has, dual sort of interfaces to dual kind of controllers, power supplies. It has NVRAM that's mirrored between those two controllers. I say controllers, but these are very lightweight by the comparison to a standard array because all the compute is really up in the compute nodes.
What does the I/O path look like? Or do you get into that later on, or?
Yeah, there is a little.
Okay.
Hold on 1 minute. Then there is a sort of a breakup of the architecture kind of block diagram. So let's wait for that one.
Perfect.
Yeah. Was there another question? No. Okay. So yes, we also claim essentially linear scaling in terms of performance as you add nodes, especially on the read side. If you have an all-flash array, for example, it comes with that fixed pi. The total performance isn't going to grow at all as you add hosts, but with the DVX being server powered with every compute node you add, it comes with more flash and more IOPS, and there's no need for any message to any RPC to leave that server to satisfy a read request in essentially all cases, right? When you are buying flash in your own server, it's because we support any server if you want. So there's you're paying commodity prices for the flash, and then we dedupe that flash, we compress the data in the flash, so the usable capacity is huge, and you just have enough to hold all the data. So everything in practice is local. We're typically 99-point-something% hit rates across the deployments in the field.
How much cache do you put in each compute node? What's your recommended amount?
It's up to you. We support up to 16 terabytes of raw flash, which, depending on your compression and dedupe ratio, could be something from 30, 50, 100 terabytes of effective capacity in every server.
When you did your 99% cache hit rate, what percentage of cache to backend storage did you use? Because I think that's important.
So it's sort of important, but in most environments, there's a lot of durable data that's not active.
Right.
And I don't by active.
Set.
No, I don't mean that. What I mean is it's not even addressable because the VM's not turned on. Right. So you have a bunch of VMs that are powered off. Well, that's not just cold data. It's like there's no chance that it's going to be accessed. So typically there's sort of 10% of the capacity that's actually in use. And what we guide our customers to do is have enough flash in the servers to hold all of that in-use data.
Okay.
Yeah.
because of that effect, there's actually a closer relationship between number of cores in the host and the flash that you'd apply. If it kind of across the VM landscape in server VMs, there's a sort of one-to-one relationship between number of VMs running and cores. Mm-hmm. Across the VM landscape, there tends to be a fairly narrow bell curve of how big the excess data is of a server VM. You know, there's a wide range, but there's also a long tail. So it's kind of, you know, usually in the 50, 100 gig thick per VM. So together, that means for this kind of configuration, it's more core related than durable data related. So you can have, if you have a quad socket server, you probably want more flash because you're probably doing more VMs.
You're stacking more VMs. You have a higher ratio of VMs to host. That makes sense. Okay. Do you know what your overhead is against CPUs for doing these data services, things like that? I mean, it's the same conversation you have with in the hyperconverged space because you're all doing it in software.
Yeah, and I'll touch on that a little more in a second. But basically, short answer, we reserve 20%, but we allow you to deploy more in insane mode. Yeah, and that is what is shown here. So here's a chart of the performance in the standard with the standard 20% of cores applied. But if you go to insane mode and you dedicate twice the number of cores and have appropriate flash to support it, you can get, you know, nearly 2x the IOPS out of it.
Are you going to do the demo where you hit the insane mode button? I remember seeing this now. Okay.
At least once.
All right.
Excuse me.
So
hang on to your seat.
Are you running as like a VSA, or is it in?
No, so we
internal,
run.
But like, are you in the user space, or?
Yeah, we're in more like user space, where like, if you're familiar with VMware's IO filter program, then it's kind of runs where that.
Okay.
Is. Yeah, so it's not in the kernel, which is very nice, because if there's a software glitch or you want to upgrade that software, you don't have to reboot the ESX server. You can do an upgrade with live running VMs. Let's see. If you, so to get more IOPS, you can go to insane mode. If you either don't want to devote those cores to I/O performance, or if that's not enough, then you can also, the other kind of key lever for performance management is to vMotion the VM to a server that has more resources. So if that either has more flash capacity to accommodate that VM or has more CPU available to accommodate it. And I mean, that's the sort of the easy knob for performance tuning in a VMware environment anyway. And what we do is extend that model to the storage itself. So you get more storage performance by migrating a VM to the server which has the resources to support it. By the way, this case of vMotion is really the only case where the compute nodes talk to each other, right? The architecture is really conceived with the idea that the compute nodes do not chatter back and forth with each other. It's a much closer to a normal traditional array server model where you have storage and compute. And the compute doesn't talk to each other. But in the case of vMotion, where you have all of that, the active data for that VM is in the flash of the originating host, you don't want to then pull that out of disk. So we do migrate the data from directly flash to flash so that it follows the VM wherever it is. So that architecture that allows the host to run independently of each other is what allows us to support the heterogeneity of hosts. It allows for example, different host configurations with very different styles of workloads to happily coexist in the same DVX. And so you may have one configuration of a compute node for analytics. You may have another, maybe beefier configuration for a SQL server or possibly a data warehouse, which has a lot, is out on that tail of capacity needed by VMs. You can just deploy a server with the appropriate flash capacity for that workload, the appropriate CPU for that. And if you run your workload on that server, that workload will get all of the resources of that beefy server for itself. It's not either sharing out those resources to workloads running on other servers, nor is it dependent on other possibly slower servers for its own performance. Every server's sort of performance and capacity is a self-contained unit. It's basically as if the server's running with just local flash. It's just that that flash is wrapped in an enterprise-grade data management system. It's not just an SSD device. And this is also, by the way, what allows us to support the open converged model. Normally, you would want to lock down the configurations of those servers so that they're more tuned to each other because they're all interdependent. In our case, the servers are isolated from each other so they can be all different. And that means some of them can be Datrium compute nodes that you bought in a turnkey system, and some of them can be prior gen legacy servers or new other kinds of configured servers, and they all run happily together in that same DVX. So here's the architecture slide I promised earlier. Basically, down here, so up in the top, the inside of the compute node, every compute node has Datrium software. And that software is exporting an NFS interface. So to VMware, it sees a single NFS data store for all of the servers in that DVX. So there's shared data, vMotion works, everything works just as if there was an NFS data store shared among all of those hosts. But in fact, the NFS is terminated inside of every host. So there's no going over the wire to implement that. And then the software inside that host also does the core data management features that I mentioned, like fingerprinting for deduplication, compression, encryption, data integrity checksumming, and erasure code. And it does that right when the data comes into the system. And data is also synchronously written to NVRAM within the data node. So before the write is acknowledged to the VM. So if a host ever fails, there's zero data loss because every write is safely in the compute node.
How much RAM is?
Sorry, the data node.
How much RAM is in the data node?
64 gigs.
And the back-end disks are...
But that's total, right? So NVRAM is a few gigs of that. Yes.
And the back-end disks are... What kind of disks were those?
They are spinning normal
7200,
fat SATA 7200.
Okay. So
there's nothing, by the way, that says they have to be. This system is completely designed, on the host side, but also on the data node to support flash media as well. But because there's so much performance up inside the host, and you really should think of this data node as the extended retention for snapshots and that kind of thing. This is not a performance critical part of that. And so it's just more cost effective to have disk.
Would you say it's not a performance critical part even in a write-heavy environment? I mean, that.
So it is fair to say that because all the writes go through here, the write performance is ultimately that is the cap on what you're going to see, but it's not the disks. Because the writes hit, this just goes to NVRAM.
And then you sequentialize that data that's good.
That's right. And it gets erasure coded, and only very large writes are what actually go to the disk. So it's a log structured file system. And so it's really write optimized. And so the disk performance is not an issue, and all of the reads come out of flash.
Does that look familiar?
Feels like vVol a little bit. Individual network nodes on each individual host.
But a vVol is kind of a VM specific, right? This is...
Yeah, but some of the implementations, they lock in individual virtual network interfaces kind of on each individual host, so that when you do that vVol data store, it's spanned across. When you were describing it, that's what it reminds me of, is that kind of an architecture.
So being NFS, we have visibility into the individual files, the individual VM decays, and so we know what a VM is, and that allows us to do data management at a VM granularity, and Cesala will tell you a lot more about that a little bit later. Okay, yeah, so reads, data is written also to local flash, but not synchronously. It doesn't need to be because it's safely off in mirrored NVRAM. And it is deduplicated and compressed before it goes to that local flash. And as I say, essentially all of reads come out of that, either the RAM buffer or the local flash.
So for the flash, do you just support whatever the hypervisor supports? So on the slide it says vSphere, so I'm assuming NVMe, whatever the hypervisor supports, you guys will run with.
That's right. Okay. And in fact, we've had customers running with NVMe flash in the host from day one. So we have over a year in production with NVMe right now.
Is that dedupe index, is that just stored within that host, or is that?
Yeah, this dedupe index applies to the local flash, but so there's just dedupe within that flash that applies to that host. But the data pool in the data nodes is globally deduped. And so among this persistent metadata is the index for the global pool, which I alluded to earlier. And one of the cool technologies is how we manage to keep that index in RAM, even though we only have 64 gigs of RAM in the controller, which is actually another kind of key part of our secret sauce. Okay, any questions on this before I move on?
What's the protocol between the compute nodes and the data nodes? Does it look like NFS? Is it a mount point?
So there's sort of two levels of the system. To support the NFS, the namespace I mentioned is shared for the cluster. That protocol looks NFS-ish, because there's no point in getting too innovative on that. But for the bottom end, for the data pool itself, is a proprietary protocol. The hosts address each storage device individually because, as I said, the erasure coding is done up on the host. Rebuilds are done on the host. If there's a data integrity issue on a read, for example, the host will just go ahead and reconstruct that data itself because all of that RAID is running up here. So the protocols are a conversation to each of the drives individually. with a proprietary protocol designed for sharing across.
Is it a cabled interconnect? Is it a SAS backplane?
It's 10 gig Ethernet.
There we go. There we go.
Thank you.
Got it.
Should have mentioned that. Okay. So the system was designed to be easy. And that means it was designed to just work with the core, all those core capabilities turned on, so that you don't have to make choices. You don't have to say, well, do I want data reduction or do I want performance? We just say, well, how about performance with data reduction, right? So deduplication, compression, erasure coding, these features are just always on. You can't turn them off. They just get rid of those knobs altogether because it just works. And the things like the isolation make performance debugging a lot easier. And so all of these sort of architectural features of the individual DVX are what makes it easy to operate once you have it, right? So you get easier maintenance by being able to just unplug your server just as before. All of these things lead into just much simpler operational experience. Owning a DVX and managing it is nearly effortless.